Hello, everyone. Can you hear me? This is the first stream in this channel. I'm just testing a few things and then I will start reading the physics books. Okay, so I'm changing to full screen right about now. Okay, so the website I'm using is OpenStax. They give these free books. So I'll be reading them. Really wanted to learn physics. So they have these different physics book, college physics, high school physics, university physics volume 1. So what I'm planning, I'm assuming these three will be the most detailed. So I'm reading university physics volume 1. Okay. University physics is a 3-volume collection that meets the scope and sequence requirements for 2 and 3 semester calculus based physics courses. So I have finished 2 volumes of calculus and from OpenStax. I finished 2 volumes of calculus, and the third volume I'm currently reading that on my stream. So yeah, you can check that out as well. Volume 1 covers mechanics, sound, oscillations, and waves. Volume 2 covers thermodynamics, electricity, and magnetism. And Volume 3 covers optics and modern physics. The main reason I started this channel was mainly because of electricity and magnetism, because I want to get into robotics later down the line. I want to get into electronics, I mean. Well, robotics, electronics, something. Anyways, yeah, let's start with the introduction. Also, my laptop is really slow, so there will be a lot of waiting time. As noted in the figure caption, the chapter opening image is of the Whirlpool galaxy, which we examine in the first section of this chapter. Galaxies are as immense as atoms are small, yet the same laws of physics describe both, along with the rest of nature. An indication of the underlying unity in the universe. The laws of physics are surprisingly few, implying an underlying simplicity of nature's apparent complexity. In this text, you will learn about the laws of physics. Galaxies and atoms may seem far removed from your daily life, but as you begin to explore this broad ranging subject, you may soon come to realize that physics plays a much larger role in your life than you first thought, no matter your life goals. The scope and scale of physics. Okay. Physics is devoted to the understanding of all natural phenomena. In physics, we try to understand physical phenomena at all scales, from the world of subatomic particles to the entire universe. Okay. I will skip a few introductory stuff. Should I zoom in? Should I use this? I don't know. I can see it fine, but I don't know on stream how well does it show. Is this good enough? Humans have created and manufactured millions of different objects. Successive technological periods, often referred to as the Stone Age, Bronze Age, Iron Age, and so on, are marked by knowledge of the physical properties of certain materials and the ability to manipulate them. This knowledge all stems from physics, whether it's the way a rock would flake when constructing a spear point, the effect of integrating carbon with iron in South India and Sri Lanka furnaces to create the earliest high quality steel, or the proper way to combine perfectly ground and polished pieces of glass to create optical instruments. Okay, most of this is introductory. Science consists of theories and laws that are the general truths of nature, as well as the body of knowledge they encompass. Scientists are continuously trying to expand this body of knowledge and to perfect the expression of laws that describe it. Physics, which comes from the Greek physis, meaning nature, is concerned with describing the interactions of energy, matter, space, and time to uncover the fundamental mechanisms that underlie every phenomena. This concern for describing the basic phenomena is in nature essentially defines the scope of physics. Physics aims to understand the world around us at the most basic level. This Apple iPhone is a common smartphone with a GPS function. Physics describes the way that electricity flows through the circuits of this device. Engineers use their knowledge of physics to construct an iPhone with features that consumers will enjoy. Uh, okay, most of this is introductory stuff. Physics is a key element of many important disciples and contributes directly to others. Chemistry, for example, since it deals with the interactions of atoms and molecules, has close ties to atomic and molecular physics. Most branches of engineering are concerned with designing new technologies, processes, or structures within the set within the constraints set by the laws of physics. In architecture, physics is at the heart of structural ability and is involved in the acoustic, heating, lighting, and cooling of buildings. Parts of geology rely heavily on physics. What do they mean parts? Isn't like entire geology like subset of physics? Some disciples, such as biophysics and geophysics, are hybrids of physics and other disciples. Physics has many applications in the biological sciences. On a microscopic level, it helps describe the properties of cells and their environments. On a macroscopic level, it explains the heat, work, and power associated with the human body and its various organ systems. Physics is involved in medical diagnostics such as radiograms, magnetic resonance imaging, and ultrasonic blood flow measurements. From the discussion so far, it should be clear that to accomplish your goals in any of the various fields within the natural sciences and engineering, a thorough grounding in the laws of physics is necessary. The reason for this is simple. The laws of physics govern everything in the observable universe at all measurable scales of length, mass, and time. Now that it is it is easy to say, but to come to grips with what it really means, we need to get a little bit quantitative. So, before solving the various scales that physics allows us to explore, first let's look at the concept of order of magnitude. The order of magnitude of a number is the power of 10 that most closely approximates it. Thus, the order of magnitude refers to the scale of a value. Each power of 10 represents a different order of magnitude. For example, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and so forth are all different orders of magnitude, as are 10 to the power of 0, negative 1, negative 2, negative 3. To find the order of magnitude of a number, take the base 10 logarithm of the number and round it to the nearest integer. Then the order of magnitude of the number is simply the resulting power of 10. For example, the order of magnitude of 800 is 10 to the power of 3 because log 800 base 10 is 2.9. Wait a minute, which rounds to 3. Okay. Similarly, the order of magnitude of 450 is 10 to the power of 3 because log 450 is 2.6. It rounds to 3 as well. So these two are in the same order. However, the magnitude of 250 is 10 to the power of 2 because log of it is 2.39, which rounds to 2. An equivalent but quicker way to find out the magnitude of a number is to first write it in scientific notation and then check to see whether the first factor is greater than or less than 10 to the power of zero point 0.5. The idea is that root 10 is halfway between 1 and 10 on a log base scale, on a log base 10 scale. Thus, if the first factor is less than root 10, then we round it to 1. The order of magnitude is simply whatever power of 10 is required to write the number in a specific notation. On the other hand, if the first factor is greater than root 10, we would round it up to 10, and the order of magnitude is 1 power of 10 higher than the power needed to write the number in scientific notation. For example, the number 800 can be written in the scientific notation as 8 times 10 to the power of 2, because 8 is bigger than root 10. We say the order of magnitude of 800 is 10 to the power of 3. The number 450 can be written as 4.5 times 10 to the power of 2. So its order of magnitude is also 10 to the power of 3 because 4.5 is greater than 3. However, 250 written in scientific notation is 2.5 times 10 to the power of 2, and 250 is less than 3. So its order of magnitude is 10 to the power of 2. I actually have done physics A level, but there were some details I didn't know about this. The order of magnitude of a number is designed to be a ballpark estimate for the scale of its value. It is simply a way of rounding numbers consistently to the nearest power of 10. In other words, if the number differ by one order of magnitude, the one is larger than the other by about 10. This makes doing rough mental math with very big and very small numbers easier. For example, the diameter of a hydrogen atom is on the order of 10 to the power of minus 10 meters, whereas the diameter of the sun is on the order of 10 to the power of 9. So it would take roughly uh, 10 to the power of 19 hydrogen atoms to stretch across the diameter of the sun. This is so much easier to do in your head than using a more precise values of uh, 1.06 times 10 to the power of minus 10 for a hydrogen atom diameter, and 1.39 times 10 to the power of 9 for the sun's diameter. To find it would take 1.31 times 10 to the power of 19 hydrogen's atom to stretch across the sun's diameter. The vastness of the universe and the breadth over which physics applies are illustrated by a wide range of examples known as lengths, masses, and times in figure 1.4. Examining this table will give you a feeling for the range of possible topics in physics and numerical values. Good way to appreciate the vastness of range of values is in figure 1.4 is to try to answer some simple comparative questions such as the following. How many hydrogen atoms does it take to stretch across the diameter of the sun? How many protons are there in a bacterium? How many floating point operations can a supercomputer do in one day? Okay. Visit this website to explore interactively the vast range of length scales in our universe. To scale. Scroll down and up the scale to view hundreds of organisms and objects. Click on individual objects to learn more about each one. How did we come to know about the laws of the governing phenomena? What we refer to as the laws of nature, a concise description of the universe around us. They are human statements of the underlying laws or rules that all natural processes follow. Such laws are intrinsic to the universe humans did not create them and cannot change them. We can only discover and understand them. Their discovery is not a very human endeavor with all the elements of mystery, imagination, and struggle. The cornerstone of discovering natural laws is observation. Scientists must describe the universe as it is, not as we how we imagine it. Hold on. Sorry, I have to write something down. Right. What's this? Okay, we are going down the scale. Smallest thing visible. Oh my gosh, a transistor gate is this small. Okay, it even goes smaller than this. How do we figure all of this out? Top quark, neutrino. Is there nothing here? Black length, quantum foam, string, octometers. Let's see how far up we go. Oh, they added a Minecraft world as well. It's really lagging my laptop. Oh my god. Local group, oh my god. We grow cluster, Formax cluster, Sloan Great Wall, observable universe. Um, a model is a representation of something that is often too difficult or impossible to display directly. Although although a model is justified by experimental test, it is only accurate in describing certain aspects of physical system. Example is the Bohr model of single electron atoms in which electrons is pictured as orbiting the nucleus, analogous to the way planets orbit the sun. We cannot observe electron orbit directly, but the mental image helps to explain some of the observation we can make, such as emission of light from hot gases. However, other observations show that the picture in the Bohr model is not really what atoms look like. The model is quote unquote wrong, but it's still useful for some purposes. Physicists use models for a variety of purposes. Uh, for example, models can help physicists analyze a scenario and perform calculations, or models can be used to represent a situation in the form of a computer simulation. This is the Bohr model, nucleus, electrons roaming around. The word theory means something different to scientists than what is often meant when the word is used in everyday conversation. The model, which is a representation, and theory, which means To a scientist, a theory is not the same as a guess or an idea or even a hypothesis. The phrase is just a theory seems meaningless and silly to scientists because science is founded on the notion of theories. To a scientist, a theory is a testable explanation for patterns in nature supported by scientific evidence, verified multiple times by various groups of researchers. So, a theory, so my understanding is like you start with a hypothesis, which is an educated guess, and then you do experiments to test your hypothesis. Experiments. And then, if the experiment is wrong, update your beliefs. Um, we have our current beliefs about the thing. So, experiment. Um, we do experiment, and anytime the experiment fails, we update our beliefs on that thing. And then we do an experiment. Anytime it fails, we update our beliefs. Experiment updates our beliefs. After this happens many times, we end up with a theory. So, fail. Oops. I want to draw an arrow. We have a fail. So, after many passes, many, I should say, uh, no fails, we get a belief that has been tested and we are pretty confident with, but we aren't completely certain because there could be an experiment that might disprove it. So, a theory is like a belief that is not disproven, but there is lots of evidence for it. That's how I understand it, but I could be wrong. Theory is a testable explanation for patterns in nature supported by scientific evidence and verified multiple times by various groups of researchers. Some theories include models to help visualize phenomena, whereas others do not. Newton's theory of gravity, for example, does not require a model or mental image because we can observe the objects directly with our own senses. Although models are meant to describe certain aspects of a physical system accurately, a theory should describe all aspects of any system that falls within its domain applicability. In particular, any experimentally testable implication of a theory should be verified. If an experiment ever shows an implication of a theory to be false, then the theory is either thrown out or modified suitably. A law uses concise language to describe a generalized pattern in nature supported by scientific evidence and repeated experiments. So, a theory is an explanation, a law is a pattern, is a generalized pattern. What about Newton's laws? Why not Newton's theories? Often a law can be expressed in a form of a single mathematical equation. Laws and theories are similar in that they are both scientific statements that result from a tested hypothesis and are supported by scientific evidence. However, the designation law is usually reserved for a concise and very general statement that describes phenomena in nature, such as law that energy is conserved during a process or Newton's second law of motion, which relates to force and mass. Okay, so law is more general and theory is very specific. What I'm guessing. Theory, in contrast, is a less concise statement of observed behavior. A law is more general, theory is more specific, is what I'm guessing. For example, the theory of evolution and the theory of relativity cannot be expressed concisely to be considered laws. Maybe a theory is like they can't be explained in simple terms. Biggest difference between a law and a theory is that a theory is much more complex and dynamic. A law describes a single action, whereas a theory explains an entire group of related phenomena. Less broadly applicable statements are usually called principle, such as Pascal's principle, which is applicable only in fluids. But the distinction between laws and principles often is not made carefully. The models, theories, and laws we devise sometimes imply the existence of objects and or phenomena that are yet unobserved. Predictions are remarkable triumphs and tributes to the power of science. It is the underlying order in the universe that enables scientists to make such a spectacular predictions. To make such spectacular predictions. However, if experimentation does not verify our predictions, then the theory or law is wrong, no matter how elegant or convenient it is. Laws can never be known with absolute certainty because it is impossible to perform every imaginable experiment to confirm a law for every possible scenario. Physicists operate under the assumption that all scientific laws and theories are valid until a counterexample is observed. If a good quality verifiable experiment contradicts a well established law or theory, then the law or theory must be modified or overthrown completely. Study of science in general and physics in particular is an adventure much like the exploration of an uncharted ocean. Discoveries are made, models, theories, and laws are formulated, and the beauty of physical universe is made more sublime. I'm not clear what the definition of principle is. So, principle is less broadly applicable, like Pascal's principle. So, it's a generalized statement in a very specific topic. So, you're describing a phenomena in simple terms of a very specific topic. Is that what it is? Mm. Units and standard. By the end of this section, you will be able to describe how SI base units are defined, describe how derived units are created from base units, express quantities given in SI units using metrics prefixes. How long is this? As we saw previously, the range of objects and phenomena studied in physics are immense, from the incredibly short lifetime of a nucleus to the age of the Earth. We define a physics quantity either by specifying how it is measured or by stating how it is calculated from other measurements. For example, we define distance and time by specifying methods for measuring them, such as using a meter stick and a stopwatch. Then we could define average speed by stating that it is calculated as the total distance traveled divided by time of travel. Measurements of physical quantities are expressed in terms of units, which are standardized values. For example, the length of a race, which is a physical quantity, can be expressed in terms of meter or kilometer. Without standardized units, it would be extremely difficult for scientists to express and compare measured values in a meaningful way. Two major systems of units are used in the world: SI units, also known as the matrix system, and English units, uh, al- also known as imperial system. English units were historically used in nation once ruled by the British Empire and are still widely used in the United States. English units may also be referred to as the pound, foot, pound, second system as opposed to the centimeter, gram, second system. You may also encounter the term SAE, named after the Society of Automotive Engineers. Products such as fasteners and automotive tools, for example, wrenches that are measured in inches rather than the metric units, are referred to as SAE fasteners. Virtually every country in the world except for the US now uses SI units as the standard. The metric system is also the standard system agreed on by scientists and mathematicians. In any, in any system of units, the unit for physical quantities must be defined through a measurement process. These are called the base quantities for that system, and their units are the system's base units. Other physical quantities can then be expressed as algebraic combinations of the base quantities. Each of these physical quantities is then often known as derived quantities, and each unit is called a derived unit. The choice of base quantities is somewhat arbitrary as long as they are independent of each other, and all other quantities can be derived from them. Typically, the goal is to choose physical quantities that can be measured accurately to a high precision as the base quantities. The reason for this is simple. Okay, yeah. So these are the base quantities for length, meter, mass, kilometer, kilogram, time is second, electric current, ampere, thermodynamic temperature, Kelvin, amount of substance, mole, and luminous intensity, candela. I have never seen this being used, or maybe I have, but I forgot. So length, mass, second, ampere, Kelvin, mole, and candela. You're probably already familiar with some derived quantities that are formed from the base quantities. For example, the geocentric concept of area is always calculated as the product of two lengths. Thus, area is a derived quantity that can be expressed in terms of SI base units using square meters. Similarly, volume is a derived quantity that can be expressed in cubic meters. So, in terms of SI base units, we could measure it in meters per second. Volume mass density is mass per volume, which is expressed in terms of SI base units such as kilograms per cubic meter. Angles can also be thought of as derived quantities, which can be defined as a ratio of arc length subtended by two radii of a circle to the radius of the circle. This is how the radian is defined. Depending on your background and interest, you may come up with other derived quantities such as mass flow rate, kg per second, or volume flow rate of a fluid, electric charge, mass, flux, density, and so on. Wait, so electric current, isn't that like a measure of how many coulombs have passed past a particular point? Like how many in a wire? This is a wire. And let's say there's this point over here. So current would be like how many coulombs have passed this point. Or maybe I might be wrong. When we get to the electricity chapter, it would be clear to me. This is why I'm revising physics. It's been a very long time since I last learned it. I last did anything with physics. For the most part, we use SI units in this text. Non-SI units are used in few applications in which they are very common, such as measurements of temperature in degrees Celsius, the measurement of fluid volumes in liters, and the measurement of energy in elementary particles in electron volts. Whenever non-SI units are discussed, they are tied to SI units through conversations. For example, 1 liter is 10 to the power of minus 3 meter cubed. Units of time, length, and mass, the second, meter, and kilometer. The initial chapters in this textbook are concerned with mechanics, fluids, and waves. In these subjects, all pretenant physical quantities can be expressed in terms of base units of length, mass, and time. Therefore, we now turn to a discussion of these three base units, leaving the discussion of the others until they are needed later. So, first, the second. Second has a long history. For many years, it was defined as 1 over 86 400 of a mean solar day. More recently, a new standard was adopted to gain a greater accuracy to define the second in terms of a non varying or constant physical phenomenon. Because the solar day is getting longer as a result of a very gradual slowing of Earth's rotation. Cesium atoms can be made to vibrate in a very steady way, and these vibrations can be readily observed and counted. In 1967, the second was redefined as the time required for 9 million 9 billion of these vibrations to occur. Note that may seem like more precision than you would ever need, but it isn't. GPSs rely on the precision of atomic clocks to be able to give you turn-by-turn direction on the surface of Earth, far from the satellite broadcasting their location. An atomic clock, such as this one, uses vibration of cesium atoms to keep time to a precision better than that of the better than a microsecond per year. Fundamental unit of time, the second is based on sun clocks. This image looks like from this image looks down from the top of an atomic fountain nearly 30 feet tall. I want meters, not feet. The SI unit for length is the meter. Its definition also changed over time to become more precise. The meter was first defined in 1791 as 1 over 10 million of a distance from the equator to the North Pole. This measurement was improved in 1889 by redefining the meter to be the distance between two engraved lines of a platinum iridium bar now kept near Paris. By 1960, it had become possible to define the meter even more accurately in terms of wavelength of light, so it was again redefined as 1 million wavelengths of orange light emitted by krypton atoms. In 1983, the meter was given its current definition as a distance light travels in a vacuum in 1 over these many of a second. This change comes after knowing that the speed of light to be exactly this much. The kilogram. The SI unit for mass is the kilogram. From 1795 to 2018, it was defined to be the mass of a platinum iridium cylinder kept with the old meter standard at the International Bureau of Weights and Measures near Paris. However, this cylinder has lost roughly 50 micrograms since it was created. Because this is the standard, this has shifted how we define a kilogram. Therefore, a new definition was adopted in May 2019 based on a Planck constant and other constants which we will never change in value. We would study Planck's constant in quantum mechanics, which is an area of physics that describes how the smallest pieces of the universe work. The kilogram is measured on cable balance. When a weight is placed on a cable balance, an electric current is produced that is proportional to Planck's constant. Since Planck's constant is defined, the exact current measurements in the balance define the kilogram. SI units are part of the metric system, which is convenient for scientific and engineering calculation based on the units because the units are categorized by factors of 10. Table 1.2 lists the metric prefixes and symbols used to denote various factors of 10 in SI units. So iota, yocto is minus 24, iota is plus 24. Let's see from the bottom. Deci, minus deci, deca, centi, hecto, millikilo, micro, mega, pepicto, tera, hexine, atto, zepto, yocto, iota. The only rule when using metric prefixes is that you cannot double them up. For example, if you have a measurement in petameters, it is not proper to talk about mega gigameters, although mega and giga both make petameters. In practice, the only time this becomes a bit confusing is when discussing masses. As we have seen, the SI unit of mass is kilogram, but metric prefixes need to be applied to the gram because we are not allowed to double up prefixes. Thus, 8,000 kilogram is written as a megagram. Incidentally, 10 to the power of 3 is also called a metric ton. This is one of those units outside of the SI system considered acceptable for our use with SI units. So restate the mass, this mass, using a metric prefix such that the resulting numerical value is bigger than 1 but less than 1000. So we have to the power of 13, right? We have tera over here. So what example 1.1? We have this 13. Sorry, it's positive 13. We can write this as 19. You can write it like this. So 19.3 tera kg. Wait, no, what? Tera kg doesn't make sense. You have to remove the kilo, right? So it's gigagrams. No, wait. The kilo over there, this is kg. This becomes 12 becomes 15 grams. So 19.3 petagrams. Since we are not allowed to double up prefixes, we first need to restate the mass in grams by replacing the prefix symbol k with a factor of 10 to the power of 3. Replacing k, we get 10 to the power of 16. P. Yeah, 10 to the power of 16. And then instead of 1.93, you put 19.3. 1.93 times 10 to the power of times 10 petagrams. And then we do 19.3 petagrams. Unit conversions. How many chapters are there? I will try to finish all of them. We will see. Use conversion factors to express the value of a given quantity in different units. It is often necessary to convert from one unit to another. Let's consider a simple example how to convert units. Suppose we want to convert 80 meters to kilometers. First thing to do is to list the units you have and the units to which you want to convert. 80 meters. They changed it to 0.08 kilometers. Note that the unwanted meter unit cancels, leaving only the desired kilometer unit. In the explanation is kind of stretched out. A conversion factor is a ratio that expresses how many of one unit are equal to another unit. For example, there are 12 inches in 1 feet, 1609 meters in 1 mile, and so on. The distance from university to home is 10 miles, and it takes 20 minutes to drive this distance. Calculate the average speed in meters per second. First, we have to convert. Should I? Hold on. I should have Desmos on. Wait a minute. So they said 10 miles usually takes 20 minutes. So example 1.2. 20. Actually, let's do this. 60 minutes. 60 second is 1 minute. When will this load? What about the mile thing? 1609 meters in 1 mile. 9 meters in 1 mile. Right? And then 20 minutes. 6 times 2 is 12. This is 20 minutes. So calculate the average speed in meters per second. So say, so they said 10 miles. So these many meters per this many second. 13.408. Yep. How many significant figures do we use? Just 13. Converting between metric units, the density of iron is 7.86 grams per centimeter cube using under standard conditions. Convert this to kg per meter cube. Here we have to shift the decimal place around when we are multiplying by 1000 and dividing by 1000. Yeah. The dimension of a physical quantity expresses its dependence on the base quantities as a product of symbols representing the base quantities. Table 1.3 lists the base quantities and the symbols used for their dimension. For example, a measurement of width is said to have dimension. Wait, what? A measurement of length is said to have a dimension of L or L1. Measurement of mass has a dimension of M or M1. Time has T or T1. Like units, dimensions obey the rules of algebra. Thus, area is the product of two lengths, so it has the dimension L2. Oh, I see. Then speed has a dimension of length over time, so L over T. Volumetric mass density has a dimension of mass over L over 3. So symbol for dimension is length mass T. Current is I. Thermodynamic temperature is theta. Amount of substance is N. And luminous intensity is J. Physicists often use square brackets around the symbol for a particular quantity to represent the dimension of that quantity. For example, if R is the radius of a cylinder, H is its height, then we write R is L and the dimension of H is L. To indicate the dimensions of a radius and heights are both those of length or L. The importance of the concept of dimension arises from the fact from any mathematical equation relating physical quantities must be dimensionally consistent, which means the equation must obey the following rules. Every term in an expression must have the same dimension. It does not make sense to add or subtract quantities of differing dimension. The arguments of any of the standard mathematical functions, such as trigonometric functions, logarithm, or exponential functions that appear in the equation, must be dimensionless. These functions require pure numbers as input and give pure numbers as outputs. If either of these rules is violated, an equation is not dimensionally consistent and cannot possibly be correct, cannot possibly be a correct statement of a physical law. Hold on a minute. Wait, are we sure about this point? Logarithm or exponential function that appear must be dimensional. The exponential function increases the dimensions, right? But for the sine and cosine thing, let's say there is a let me think about this. Yeah, let's say there's a ball going up and down like this in a periodic way. Let's say it follows sine x. Let's say the position of the ball follows sine x. So when you it's like this. where the x-axis is the mean position, and these two are the offset. We're calculating the offset from the mean, and this is the time. Position 0 is here, and then up and down, and up and down. But the thing is, we are using time as an input of sine x. So the equation of this would be offset, which is measured in meters, is sine x, where the dimension of x is time. Where the dimension of offset is yeah, in meters. So we can use the arguments of any of the standard mathematical functions, such as trigonometric function, must be dimensionless. But we are adding a dimension quantity into sin x, right? Or in this scenario, using dimensions to remember an equation. Suppose we need a formula for the area of a circle for some computation, like many people who learned geometry too long ago to recall with any certainty. Two expressions may pop on in our mind when we think of circles: pi r square and 2 pi r. One expression is the circumference of the radius r, and the other is its area. But which one is which? Circumference, we measure circumference in one dimension, right? But area is measured in two dimensions. So this is most probably correct. Well, this is correct, I know. But I get the point they're making. Consider the physical quantities SVA and T with dimensions L, LT minus 1, LT minus 2. And T, this one is time. Determine whether each of the following equation is dimensionally consistent. S is equal to Vt plus half At square. This is dimensionally consistent. There are no trigonometric, logarithmic, or exponential functions to worry about in this equation. So we need to look at the dimension of each term appearing in the equation. There are three terms, one in the left expression, two on the right. So we look at each. All three have the same dimension, so the equation is dimensionally consistent. So, and for the next one, the technical term for an equation like this is nonsense. Okay, for the next one, so the dimensions don't match. For this one, however, it has a trigonometric function in it. So first we check that argument of sine function is dimensionless. So we have this cancels out, get one. The argument is dimensionless, so far so good. Now we need to check the dimensions of each of the two terms. So one, this is LT to the power of 1, negative 1. Two terms have different dimensions, meaning the equation is not dimensionally consistent. Oh, what about my scenario? If someone in the chat, I'm not reading the chat right now, but I've read it upstream, off stream. If someone can explain this part, like a ball moving periodically, we can use time to measure the position, right? So you can't say, so you can, in fact, use trigonometric functions. One further point that needs to be mentioned is the effect of the operations of calculus on dimensions. We have seen that dimensions obey the rules of algebra just like units, but what happens when we take a derivative of one physical quantity with respect to another, or integrate a physical quantity over another? The derivative of a function is just a slope of tangent line to its graph. Slopes are ratios. So for physical quantities v and t, we have that the dimension of the derivative of v with respect to t is just a ratio of the dimension of v over t. So dv over dt, the dimension of this entire thing, is the dimension of this divided by the dimension of this. For the integral is opposite. We are multiplying t, we are multiplying v over, we are multiplying small amount of t's with the appropriate v, with the v in that particular t. So then we are left dimension of v times dimension of t. Since integrals are just sum of products, the dimension of the integral of v with respect to t is simply the dimension of v times the dimension of t. Estimates and Fermi calculations. On many occasions, physicists and other scientists, engineers need to make estimates for a particular quantity. Other terms sometimes use guesstimates, order of magnitude approximations, back of the envelope calculations, whatever. The physicist Enrico Fermi mentioned earlier was famous for his ability to estimate various kinds of data with surprising precision. While that piece of equipment fit in the back of the car, will that piece of equipment fit in the back of the car, or do we need to rent a truck? Estimating does not mean guessing a number or a formula at random. Rather, estimation means using prior experience and sound physical reasoning to arrive at a rough idea of a quantity's value. Because the process of determining reliable approximation usually involves the identification of the correct physical principles and a good guess about the relevant variables, estimating is very useful in developing physical intuition. Estimates also allow us to perform sanity checks on calculations or policy proposals by helping us rule out certain scenarios or unrealistic numbers. They allow us to challenge others as well as ourselves in our efforts to learn truth about the world. Many estimates are based on formulas in which the input quantities are also only known to limited precision. As you develop physics problem solving skills, you also will develop skills at estimating. Get big lengths from smaller lengths. In estimating lengths, remember that anything can be a ruler. Thus, imagine breaking a big thing into smaller things. Estimate the length of one of the smaller things and multiply to get the length of the big thing. Get areas and volumes from lengths. In dealing with an area volume of a complex object, introduce a simple model of the object, such as a sphere or a box. Then estimate the linear dimensions. First, uh, estimate the linear dimensions first, such as radius of a sphere or length, width, and height of the box, and use the estimates to obtain the volume or area from standard geometric formulas. If you happen to have an estimate of an object's area or volume, you also do the reverse. That is, use geometric formulas to get an estimate of its linear dimensions. Get masses from volumes and densities. In estimating masses of objects, it can help first to estimate its volume and then to estimate its mass from a rough estimate of its average density. For this, it helps to remember that the density of air is around 1 kilogram per meter cube. Density of water is 10 to the power of 3 kilogram per meter cube. And the densest everyday solids marks out at around 10 to the power of 4 kilogram per meter cube. If all else fails, bounded. For physical quantities for which you do not have a lot of intuition, sometimes the best you could do is think something like, well, it must be bigger than this or smaller than that. For example, suppose you have is the estimate you suppose you need to estimate the mass of a moose. Maybe you have a lot of experience with moose and know their average mass offhand. If so, great. But for most people, the best they can do is think of something like it must be bigger than a person and less than a car. One significant figure is fine. There is no need to go beyond one significant figure or one digit in the coefficient of an expression in scientific notation. When doing calculations to obtain an estimate, in most cases, the order of magnitude is good enough. Does this make any sense? Last check to see whether your answer is reasonable. How does it compare with the values of other quantities with the same dimensions that you already know or can look up easily? Okay. Question they asked was estimate the total mass of oceans on Earth. They got 3 times 10 to the power of 3. No, wait. Now we just need to put it all together. I think the advice one significant figure is fine. What did they end up with? 9 times 10 to the power of 20. I should not have spent too much time on that chapter. Significant figures. By the end of this, figure 1.11 shows two instruments used to measure the mass of an object. The digital scale has mostly replaced the double pan balance in physics labs because it gives much more accurate and precise measurements. Or what exactly do we mean by accurate and precise? Aren't they the same? In this section, we examine in detail the process of making and reporting a measurement. Science is based on observation and experiment, that is, on measurements. Accuracy is how close a measurement is to the accepted reference value for that measurement. For example, let's say we want to measure the length of standard pen to paper. The packaging in which we purchase the paper states that it is 11 inches long. We then measure the length of the paper 3 times and obtain the following measurement: 11.1, 11.2, and 10.9 inches. These measurements are quite accurate because they're very close to the reference value of 11 inches. In contrast, if we had a measurement of 12 inches, our measurement would not be very accurate. Notice that the concept of accuracy requires that an accepted reference value be given. The precision of measurements refer to how close the agreement is between repeated independent measurements, which are repeated under the same condition. Consider the example of paper measurements. Precision of measurements refer to the spread of measured values. One way to analyze the precision of measurements is to determine the range or difference between the lowest and highest measured values. In this case, the lowest was 10.9, the highest was 12.2. Thus, the measured value deviated from each other by at most 0.3 inches. These measurements were relatively precise because they did not vary too much in value. However, if the measurement value had been 10.9, 11.9, and 11.1 and 11.9, the measurement would not be very precise because there would be significant variation from one measurement to another. Notice that the concept of precision depends only on the actual measurements acquired, does not depend on the accepted reference value. So low accuracy, high precision, high accuracy, low precision. The precision of a measuring system is related to the uncertainty in the measurement, whereas the accuracy is related to the discrepancy from the accepted reference value. Uncertainty is a quantitative measure of how much your measured value deviate from one another. There are many different methods of calculating uncertainty, each of which is appropriate to different situations. Some examples include taking the range or finding the standard deviation of the measurement. Discrepancy is the difference between the measured value and a given standard or expected value. If the measurements are not very precise, then the uncertainty of the values is high. The measurements are not very accurate, then the discrepancy of the values is high. Recall our example of measuring paper length. We obtained a measurement of 11.1, 11.2, and 10.9. The accepted value was 11. We might average the three measurements to say that our best guess is 11.1 inches. This case, our discrepancy is zero point 0.1 inches. Discrepancy is how far away, how inaccurate we are. Uncertainty is how not precise we are. So zero point 0.1 provides a quantitative measure of our accuracy. We might calculate uncertainty in our best case by using half of the range of our measured value. So 0.15 inches. So the range was zero point 0.3, half of it is 0.15. Then we would say the length of paper is 11.1 inches plus minus 0.15 inches. The uncertainty in measurement A is often denoted as delta A. So the measurement result would be recorded as A plus minus delta A. Returning to our paper example, the measured length of the paper could be expressed as 11.1 plus minus 0.15 inches. Since the discrepancy of zero point 0.1 inches is less than the uncertainty of 0.15, we might say that the measured value agrees with the accepted reference value within experimental uncertainty. Okay, wait. So if the uncertainty, let's say uncertainty range was very long, and the what's the other word? Discrepancy. The value we collected was longer than that. Hold on, let me see. Then it's very difficult to say that the measured value agrees with the accepted reference. That the measured value agrees with the accepted reference. But if it's small, small discrepancy, high, high uncertainty, the measured value would likely be within the accepted range. We might say the measured value agrees with the accepted reference to within experimental uncertainty. Some factors that contribute to uncertainty in a measurement include the following: the limitation of the measuring device, the scale of a person taking the measurement, irregularities in the object being measured, any other factors that affect the outcome. In our example, such factors contributing to the uncertainty could be the smallest division on the ruler, 1 over 16 inches. The person using the ruler has bad eyesight. The ruler is worn down on one end, or one side of the paper is slightly longer than the other. At any rate, the uncertainty in a measurement must be calculated to quantify its precision. If a reference value is known, it makes sense to calculate the discrepancy as well as to quantify its accuracy. Another method of expressing uncertainty is as a percent of measured value. If a measurement A is expressed within uncertainty delta A, percentage, the percent uncertainty is defined as this divided by this times 100. Okay. Grocery store sells 5-pound bags of apple. We obtain the following measurement: 4.8, 5.3, 4.9, 5.4. So the average is 5.1. right? Hold on. 4.8 divided by 4. Is it like this? It's 5.4. So we have 5.1. This is the precision of our measuring system is related to uncertainty in the measurements, whereas the accuracy is related to discrepancy. We might average the three measurements to say our best guess is 11.1 inches, since our discrepancy is 11.1 minus 11, 0.1. Okay. Discrepancy here is also 0.1, right? 5.1 minus 5. And then the range is 5.4 minus 4.9 divided by 2. So we have 0.25. No, wait. It's 4.8. What is the percent uncertainty of the bag's weight? So 0.3 divided by 5.1, right? We get 5.9 or 6%. Uncertainty exists in anything calculated from measured quantities. For example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties. How big is the uncertainty in something you calculate by multiplication or division? The measurements going into the calculation have small uncertainties, then the method of adding percents can be used for multiplication or division. This method states that the percent uncertainty in a quantity calculated by multiplication or division is the sum of the percent uncertainties in the items used to make the calculation. For example, if a floor has a length of 4 meters and a width of 3 meters, with uncertainties 2% and 1% respectively, the area of the floor has uncertainty of 3%. So, percent uncertainty in a quantity calculated by multiplication and division is the sum of the percent uncertainties in the items used to make the calculation. Okay, so area. So, for example, area is a quantity calculated by multiplication of two lengths. So, the percent uncertainty of area, which is calculated by multiplication, is the sum of the percent uncertainties of the two lengths. All right. So, 3%. So, percent uncertainty of area in this case here will be the sum of the two percent uncertainties of the length. So 2% and 1%. You add them, we get 3%. If we, hold on, let's get rid of these. Let's get rid of these. If we have a measured quality A plus delta A and another quantity A plus delta B, if we multiply them, we get AB A delta B, B delta A. Delta B delta A. And the percent quantity is, let's call it PA. What was I thinking? Um, the percentage here, this here. I don't know what I was thinking of doing something. Yeah, I wanted to know why the percentages are added. That's what I was thinking. If we multiply them, we get this, and then the error is this, right? And the percentage uncertainty is what? Would it be all this divided by AB? Let's see. The thing I'm trying to figure out is why do we add them, add the uncertainties? This is the percentage uncertainty. If we add these two, we get less B. If we add these two, we get percentage A. Multiply both sides with, yeah, we get this, right? Um, we multiply both sides with B and we multiply this both sides with A and then we can add them. So we have this. But this and this are not the same because of this. So when we do multiply them, we get this as the percentage uncertainty, which is different from adding the percentage uncertainty directly. I mean, it's almost same except for this part, but this thing over here is very close to zero. You would expect them to be close to zero. So these two are approximately equal. That's why you're allowed to add the percentage uncertainty. But I could be wrong. So, chat has anything, please inform me. An important factor in the precision of measurement involves the precision of the measuring tool. In general, a precise measuring tool is the one that can measure values in very small increments. For example, a standard ruler can measure length to the nearest 100 millimeter, whereas a caliper can measure length to the nearest 0.01 millimeter. The caliper is more precise measuring tool because it can measure extremely small differences in length and more precise the measuring tools. The more precise the measurements. Wait, the more precise the measuring tool, the more precise the measurements. When we express measured values, we can only list as many digits as we measured initially with our measuring tool. For example, if we use a standard ruler to measure the length of a stick, we measure it to be 36.7 centimeters. We can't express this value as 36.71 centimeter because our measuring tool is not precise enough to measure a hundredth of a centimeter. It should be noted that the last digit in the measurement value has been estimated in some way by the person performing the measurement. For example, the person measuring the length of a stick with the ruler notices that the stick length seems to be somewhere between 36.6 centimeter and 36.7 centimeters. Hold on. So let's say we have a ruler over here. We have a ruler. There's a mark over here. There's 36 over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 37. 37. Right. So the stick, he has a stick, and the end of the stick is like over here somewhere. So 1, 2, 3, 4, 5, 6, 7. Yeah. It's between the 6 and 7 mark somewhere. So this part is at 0. This is at 0. This is at 6 and between 6 and 7. 36.6 to 36.7. So so and he or she must estimate the value of the last digit using the method of significant figures. The rule is that the last digit written down in a measurement is the first digit with some uncertainty. Okay, so we are certain that it's below 36.6 and above, sorry, in between 36.6 and 36.7. So this is the lower, this is the upper. This part we are certain about. So we can write this as 6.5 plus or minus centimeters. You can write it like so. The last digit is the uncertain, has the uncertainty. To determine the number of significant digits and a value, start with the first measured value to the at the left and count the number of digits through the last digit written on the right. For example, the measured value 36.7 has 3 digits or 3 significant figures. Significant figures indicate the precision of a measuring tool used to measure a value. So the rule is that last digit written down in a measurement is the first digit written with some uncertainty. Special consideration is given to zeros when counting significant figures. The zeros in 0.053 are not significant because they are placeholder to indicate the decimal point. There are two significant figures. The 0 in 10.053 are not placeholders, they are significant. This number has 5 significant figures. The zeros in 1300 may or may not be significant, depending on the style of the writing numbers. They could mean the number is known to the last digit, or they could be placeholder. So 13 could have 2 or 3 or 4 significant figures. To avoid this ambiguity, we should write 1300 in scientific notation as 1.3 times 10 to the power of 3, or 1.30 times 10 to the power of 3, or 1.300 times 10 to the power of 3. So the digits over here would be what the significant digits. This way we know that these two zeros are significant and not just placeholder, depending on whether it has 2 or 3 or 4 significant digits. Zeros are significant except when they serve only as a placeholder. When combining measurements with different degrees of precision with mathematical operations of addition, subtraction, multiplication, or division, then the number of significant digits in the final answer can be no greater than the number of significance in the least precise measured value. There are two different rules, one for multiplication division and other for division subtraction, addition subtraction. Number of significant digits in the final answer can be no greater than the number of significance in the least precise measured value. Okay. So let's say they give us a question where the distance traveled is like these many uh, meters, and then the number of second was like this, these many second. Our final answer will be two significant digit, not this many significant digit. You're going by the least precise value. For multiplication and division, the result should have the same number of significant figures as the quantity with the least number of significant figures entering into the calculation. For example, the area of a cylinder can be calculated from its radius using A is equal to pi r squared. Let's see how many significant figures the area has if the radius has only two. Say r is equal to 1.2. Using a calculator with 8-digit output, we would calculate this. So pi is infinitely long and we have 1.2. But because the radius has only two significant figures, it limits the calculated quantity to two significant figures. So the area is 4.5. For addition and subtraction, the answer can contain no more decimal places than the least precise measurement. Suppose we buy 7.56 kg of potatoes in a grocery store as measured with a scale with precision 0.01 kg. Then we drop off 6.052 kg of potatoes at your laboratory as measured by a scale with precision 0.01 kg. Then we go home at 13.7 kg of potatoes as measured on by a bathroom scale with precision 0.1 kg. How many kilograms of potatoes do we now have? And how many significant figures are appropriate in the answer? Mass is found by simple addition and subtraction. 7.65 minus this plus this, we get this. But we take the least significant figures. Then the least precise measurement, right? Least number of significant figures, no more decimal places than the least precise measurement. So final answer must also be expressed to 0.1 decimal places. Thus, the answer is rounded to the 10th place, giving us 15.5, 15.2. So the addition and division is the least number of uh, least precise measurement. For multiplication and division, we take the our final answer would take the answer would have the what am I saying? For multiplication and division, the result should have the same number of significant figures as the quantity with the least number of significant figures entering into the calculation. Okay, I think I understand. Let's say we have many significant figures. Then we are adding it with the placeholder value. This has two significant figures. This has 1, 2, 3, 4, 5. When we add these two, we only include like one decimal place. So we take the least decimal place, the least precise, and then we don't add the rest. So the final answer would be 0016, right? But this part is like removed because we take the least precise. In this text, most numbers are assumed to have three significant figures. Furthermore, consistent numbers of significant figures are used in all worked examples. An answer given to the three digits is based on input cut to at least three digits. For example, if the input has fewer significant figures, The answer will also have fewer significant figures. Care is also taken that the number of significant figures is also reasonable for the situation posted. Solving problems in physics. Problem solving skills are clearly essential to success in quantitative course in physics. More importantly, the ability to apply broad physical principles, usually represented by equations, to specific situations is a very powerful form of knowledge. It is much more powerful than memorizing a list of facts. Analytics cannot be made long enough to contain every possible circumstances. So, strategy examine the situation to determine which physical principles are involved. It often helps to draw a simple sketch at the outset. Make a list of what is given or can be inferred from the problem as stated. Identify exactly what needs to be determined in the problem. Determine which physical principles can help you solve the problem. The solution stage is when you do the math, substitute the knowns, enter the appropriate equation, obtain numerical solutions complete with units. After having done the math in the solution stage of the problem solving, it is tempting to think you are done. But always remember that physics is not math. Rather, in doing physics, we use mathematics as a tool to help us understand nature. So, after you obtain a numerical answer, you should always assess its significance. Check your units. If the units of the answer are incorrect, then an error has been made and you should go back over your previous steps to find it. One way to find the mistake is to check all the equations you derive for dimensional consistency. However, be warned that correct units do not guarantee the numerical part of the answer do not guarantee the numerical part of the answer is also correct. Check the answer to see whether it's reasonable. Check to see whether the answer tells you something interesting. Okay, so key terms: accuracy, the degree to which the measured value agrees with the accepted reference. Uh, English units, kilograms. Is there anything used to express the precision of a measuring tool used to measure a value? And certainly a quantitative measure of how measured value deviate from one another. Nice. So I'm going to end the stream here. And should I do the problems? Well, not for this chapter. Okay, I will just skip this one. Maybe for the next chapter, I will start doing the problems. How do I close this? Anyways, we have vectors. So this is what I will be doing next stream. I already did vectors in the calculus course, vector based function in calculus 3, but this would be a uh, good revision. Anyways, I will end the stream here. Hold on, we have mechanics, waves and acoustics. Okay, this is going to be long. Right then, I will end the stream here. And yeah, I will see you guys in the next stream when I do the vectors section. Yeah, so see you guys next time. Bye.